Welcome to Chapter 1, The Problem Domain, where we ask ourselves, what are we really up against when we consider software globalization? The short answer? We're basically dealing with language encountering technology. This simple answer begets many questions, including the seemingly simple, what is language? You might think of language as a bunch of words inside a dictionary, a book collecting dust that you only buy once every 30 years. You might think of language as something fairly static. That would be a mistake. Language, in fact, is absolutely not static. Consider this picture showing basically the history of humanity. By analyzing minute differences in DNA, by taking a look at my DNA versus the DNA of a Lebanese person or the DNA of a Chinese person, there will be some minute differences. And by analyzing these little differences, we can map the history of humanity. This map points to Homo sapiens originating some 300,000 years ago, somewhere in the middle of Africa. During that time, our DNA has changed by only 0.03%. Consider that man and monkey differ by 5%, although individual results may vary. Interestingly enough, we can build a very similar map, not by looking at DNA, but by looking at language. By studying words and sounds and grammatical structures, we can determine what languages came from what other languages and rebuild the history of language. This exercise gives us roughly the same picture as DNA mapping and leads us to the same conclusion. Humanity originated somewhere in the middle of Africa. The point here is that language is alive. It's created by people for people, passed on through family, trade, love, and even war. Religion, in particular, has been a powerful force in spreading language. Today, there are over 6,000 languages, but fewer than 25% have writing systems. Half, or nearly all, could disappear this century. Some already have just one fluent speaker left. But new languages are also born. In the U.S., Spanglish blends Spanish and English. In India, Hinglish mixes Hindi and English. These hybrids are growing and thriving, not fading. Languages can also be revived. Groups like UNESCO and the Rosetta Project work to preserve endangered ones. And Hebrew was successfully brought back to life in the 20th century. There are also efforts to revive Aramaic, the ancient language of Jesus, still spoken in a few Syrian villages. Back in 1999, 57% of Internet users were English-speaking. That dropped to 43% in 2001, then 35% in 2003. As of today, English accounts for 25% of the online population, while Chinese has risen to 19%. You could ask yourself, how far can this go? Well, if every single person in the entire world was connected, English users might represent only a measly 5%. This table shows the top 16 languages in the world, covering a bit more than 50% of human population. Seeing Chinese at the top is no big surprise. However, among the top languages, we find Arabic, Hindi, and Bengali. These languages are some of the most difficult languages to deal with on a computer. So, there's no easy way out. Internationalization ultimately means there's a lot of work ahead, because these difficult languages are not going to go away. Right now, they might not represent the most economically significant segment of the population, but that, of course, changes on a monthly or yearly basis. Not so long ago, no one would have thought of India as an economic superpower. Now the country is recognized as one of the most important destinations for outsourcing, and as incomes rise, so does consumption. Humanity, like language, is not static. This table also shows that only 4.9% of humanity are native English speakers. This seems a bit extreme. You might be thinking that surely the majority of people have a working knowledge of English. But studies have shown that only 20 to 25% of world population speaks English, and 90% of that number still prefer software and websites in their language. Another interesting thing we can see in this table is the fact that English is established in 137 countries and Arabic 59. And I am happy to say that French comes third, with 54 countries. Before going any further, let's define some common abbreviations. Internationalization is often abbreviated I-18N because the word internationalization has 20 letters. That is, there are 18 letters between the initial I and the final N. Likewise, localization has 12 letters. You get the idea. And here's a preliminary rough definition of these terms. Internationalization is about generalizing software to support multiple cultures, and localization is essentially about translating software. Internationalization is more about functional aspects, while localization is more about textual aspects. We'll see a lot more about this later. Let's see now what happens when language meets technology. Whether your product is a desktop software, a website, or a mobile app, programmers spend most of their time developing new features. Feature after feature after feature. And then, when comes the time to add language, we might think that it's just another feature, and a small one at that. But it's not. Language, in fact, is an entirely new architectural dimension that can affect all the features, all layers, and all tiers of your product. Language will affect character sets and fonts. It will affect how data is sorted and how messages are displayed. It can affect the user interface, the business logic, the database schema. It can potentially affect all components of your product and the data paths between them. And not only does language affect all your features, but it affects the entire development process. The language dimension means that requirements will now become multilingual requirements. How will you find out what you need to do to meet users' needs in Japan, Germany, or China? The usual mistake is to presume that they can make do with the same thing the English users have. Documentation now becomes multilingual documentation, and documentation can be internationalized just as code can be internationalized. It's called writing for translation. It applies to web pages as well as to PDF files. Using the right tools and appropriate processes can save 20 to 30% of document translation costs. And remember, this is where the bulk of the translation cost resides. Testing becomes multilingual testing. How will you test your product in 15 or 20 languages? You will need native language speakers, native language operating systems and browsers, and an optimal way of using these resources to provide the most useful test results. Efficient multilingual testing requires proper planning. And finally, we have international customer support. Customer support around the world in various time zones and in various languages. How will that work? How will your English experts understand the problems of Chinese users? And still, there's more. Beyond research and development, language and culture will affect the entire business process. How you market and sell will vary by country. The sponsors you choose, for example, will it be Serena Williams or a soccer superstar? Most countries have complex privacy laws that you must follow. Some also have mandatory requirements for software. The way you negotiate contracts, collect payments, and deal with banks also varies by country. And finally, even if you only have a small support team in country, you still have to deal with the local employment laws and culture. In short, language is not just another feature. Language and culture constitute the pervasive globalization dimension that affects the entire business process. It'll affect how you design, develop, and test. It'll affect how you market, sell, and support your products, be they websites, desktop software, or mobile apps. Everything that you do will be impacted by language and culture. Language, fundamentally, is communication. You all know the age-old conundrum. If a tree falls in the forest and no one is around, does it make a sound? Along the same lines, if a word is never written or uttered, does it really exist? The only goal of language is to allow communication. Language is nothing without communication. So, we ask ourselves, what is communication? This slide shows a simple model. Communication is an exchange of information between a source and an audience. The information circulates over a media, air in the case of voice, and language is the agreed set of symbols used to represent the information. One thing this model tells us is that every instance of communication has an audience, and that it is the needs of the audience that determine whether to translate or not. This is important because knowing the audiences for your product and knowing their language requirements will allow you to save on translation costs later. So, if language is communication, this means that all text strings in all programs are messages waiting to happen, and every one of these messages has a source and an audience. Most strings are messages sent from the program to the user. Keyboard commands are messages sent to the program. System logs may be messages for customer support staff. Even comments are a form of message. And sometimes software components send messages to other components, wrapped in XML, say. The XML tags do not need to be translated if both source and audience speak the same XML. An important business question that always comes up is, do we translate or not? Knowing the audience for each message will allow you to implement the business decision, whatever it may be. Now, let's get down to details. The main question a developer or localizer will have is, what changes from one language to the next? If this software is going to work in other languages, what do I have to deal with? Clearly, the first thing is that the words will be different. More importantly, the size of those words will be different. When English is translated to most other languages, the translation is longer. The text expands. Rates of expansion vary widely depending on language. For example, an English text translated into German may expand by as much as 20% overall. However, individual words may expand by a much larger percentage. For example, the expansion factor between redo in English and the German translation wiederherstellen is 400%. Here's an actual example, this time from PowerPoint. Save as web page in English becomes enregistrer en tant que page web in French. You can see here that if we wanted to add a shortcut, we wouldn't have enough space. This is trivial stuff, pretty simple. Things get bigger in other languages. So what? The fact is, the whole issue of dealing with resizing of layouts can be one of the major parts of an internationalization project. A lot of problems arise when text gets truncated, when things are not the right size, and text doesn't fit in the allotted space. A lot of time can be wasted solving these simple but persistent problems. The grammar is also different from one language to the next. For example, in French, the adjectives are often after the noun rather than before, and, like nouns and articles, they have gender and number. For example, if we were describing a car instead of a product, the adjective would be wert instead of wer. In German, verbs often turn up at the end of a sentence. For example, sent Monday in English becomes Montag gesendet in German. This is significant for software because it means that the order in which messages will display their variables can vary from one language to another. This difference will almost invariably have an impact on existing software. Capitalization rules also vary. In English, French, and German, sentences begin with a capital. But in English, however, the days of the week are capitalized, whereas in French they are not. And in German, all nouns are capitalized. Characters are also different from one language to the next. English does not use accents. French, Spanish, and German do. To give you an example of how subtle problems can creep in, look carefully at this slide. You'll notice that the N tilde and the O acute are overlapping. That's a kerning problem with the Palatino font. This might come as a surprise, but the point is, in internationalization, a surprise is not surprising. What you have to understand is software is tested in English, and even then, these days, not so well. But when you leave the English language, the amount of testing that goes into software is much less significant. Not that it should be, but that's what happens. So, in fact, in the internationalization space, a lot of things that should work don't work perfectly the way you expect them to. Understand that in this example, I'm not doing anything extraordinary. I'm not using a Korean font on Arabic windows. I'm using regular English windows with a regular Palatino font, and all I did was type a bit of Spanish. And there's already a problem? This is typical. So you can imagine the kinds of problems that will arise with more esoteric languages. There will be issues because products are not properly tested in other languages. Not only do characters change, but their number also changes, and that is even more important. For English, you're all familiar with the 7-bit ASCII set, which holds 128 characters. For European and Middle Eastern languages, a number of national and international standards have been developed. Many of these are 8-bit character sets with 256 characters, where the lower 128 characters are identical to ASCII. But now consider Asian languages. Asian languages contain 10, 20, even close to 70,000 characters, for example in Taiwan. That's a lot of characters. The sheer number of characters represents the fundamental challenge of dealing with Asian languages. Because there is a large number of Asian characters, typing them in is no easy task. To manipulate the characters, all your variables and data paths will need to be 2 bytes or even 4 bytes wide in some cases. And when it's time to display them, you'll need very large fonts, again because there are so many characters. Now, you might be hoping that the so-called Arabic numbers, which I'm calling European here, would be recognized everywhere in the world, and they are. However, the fact that they are recognized everywhere in the world doesn't make them the preferred numbers for local use. Having been there, I can certify that in Saudi Arabia, you will see Arabic Indic numbers used as page numbers in books and newspapers. You will also see them on license plates of cars or the floor number buttons in elevators. But European numbers are also used in the Arabic world. So there you have to deal with 2 sets of numbers simultaneously. The punctuation also changes from one language to the next. Here we have the ever-provincial statement, "Why can't they all speak English?" Might as well ask, "Why can't they all speak Spanish?" However, if you ask that question in Spanish, there will not only be a question mark at the end of the question, but there will also be an inverted question mark indicating the beginning of a question. Next, we have, "Why can't they all speak Greek?" Now the punctuation at the end of the question looks a bit like a semicolon. Well, in fact, it looks exactly like a semicolon, but it's not, and it's not a typo. What you are looking at is a Greek question mark. In the Unicode character set, the Greek question mark and the English semicolon are 2 different characters, each with their own distinct code. They may look the same, but they are conceptually different. In Arabic, the fact that the question mark faces the other way is not entirely surprising. However, in Hebrew, the question mark faces the same way as in English. In fact, the Hebrew text simply reuses the ASCII question mark. Finally, in Chinese you'll notice that the question mark is surrounded by a lot of white space. That's because in Chinese traditional typography, every character occupies a box of the same size, as shown here. That's why they created double-wide versions of the ASCII characters. This one is called an ideographic question mark. There are also ideographic versions of semicolon, colon, period, and more. Why all these differences? The reason we see all these differences between languages is basically because they have different writing systems, which are called scripts. Scripts are the set of rules that determine how languages are written. The script covers what the letters look like, if they have case, whether they have accents, the direction they are written in, whether they represent ideas, syllables, or individual sounds, etc. You have on the left some examples of scripts. Let's consider now how scripts relate to language. Generally, the same script is used to write many languages. For example, the Latin script is used to write English, French, German, and in fact, there are hundreds of languages today that are written with the Latin script. In a similar way, the Arabic script is used to write Arabic, Farsi, and Urdu. It's important here not to confuse the Arabic script with the Arabic language. They have the same name in this case, so confusion is easy, but the Arabic script is not the same thing as the Arabic language. The Arabic script defines the basic writing rules and the set of letters. The Farsi and Urdu languages, in fact, have a few extra Arabic letters that are not available in the Arabic language, just like French and Spanish have a few letters more than English. Note also that the Arabic script was once used in Turkey and Malaysia. Both the Turks and the Malays have been migrating their writing system to the Latin script. Devanagari is a script used in India. There are a number of languages, for example Hindi and Sanskrit, which are written in the Devanagari script. Interestingly enough, there was a language called Hindustani 100 years ago, which, at the time, was written both in the Arabic and Devanagari scripts. That is, the same words were written with different symbols, but they were the same words. The evolution of the language followed religious lines. The Muslims opted for the Arabic script, and Urdu appeared. The Hindus chose the Devanagari script, and the Hindi language was born. That means that when Urdu, spoken in modern-day Pakistan, and Hindi, a language of India, were created 100 years ago, the spoken languages were identical, but the written languages used different scripts. 100 years later, some new words have appeared. There's been a few semantic shifts, but essentially, the languages are very similar. Cyrillic also is used for a variety of languages, including Russian and Ukrainian. And Serbian, finally, is an interesting case because it is a unique language today that is still written in two scripts. Serbian can be written both in Latin and Cyrillic scripts. In fact, if you go into downtown Belgrade today, you can pick up a newspaper rendered in Latin script or a newspaper rendered in Cyrillic script. You can even pick up a newspaper that has a mixture of Latin and Cyrillic. Some scripts have case, as Greek and Cyrillic do on this slide. For other writing systems, the notion of uppercase and lowercase is moot. Arabic and Chinese, for example, do not have case. So if a programmer subtracts 32 to normalize a letter to uppercase, some text will be destroyed. And some scripts have three cases. That is, there's not only lowercase and uppercase, there is also a title case. There are a very small number of characters today in Unicode that require the concept of title case, but this particular character, DZ, is one of them. What you are looking at is not two separate characters, but rather a single character that needs two symbols to be displayed, that is, a digraph. Thus, the DZ digraph, which is a single character in the Serbian, Croatian, and Slovak alphabets, has a lowercase version, an uppercase version, and a title case version, and these are all three distinct characters in Unicode. If you're wondering what title case is good for, consider the word džungla, which means jungle in Croatian, as shown in the screenshot from Google Translate. The table below shows the sentence, I live in the jungle, in lowercase, in uppercase, and as title, that is, in title case. The red underbars show the extent of the individual characters. What this means for software is that any code that uppercases the first character of a sentence or word will need to be fixed. Let's take a look now at some of the characteristics of Asian scripts. The Chinese invented the Han ideographic script, which they called Hanzi. The Japanese and Korean also found this to be a good idea and basically adopted the Chinese system, which they called Kanji in Japan and Hansa in Korea. Note that the Koreans moved to a purely phonetic system called Hangul in the 15th century, so today Hansa is rarely used in Korea. An important point is that an ideographic script cannot stand alone. It needs a phonetic script to go with it. The reason is that there's virtually no one in the world who knows all 70,000 or more Chinese characters. When a Chinese person sees a brand new character, he or she will not know what it means and will also not know how to pronounce it. Our words, our English words, are written with letters that represent sounds, so our words tell us how to pronounce them, more or less. but ideographic characters represent mostly ideas. How to pronounce them must be known and memorized. So that's why a phonetic script is necessary, to explain the pronunciation of unknown characters. The phonetic script is used in schools, for example, to teach the language. So the Chinese have the Bopomofo phonetic script composed of a mere 37 characters, representing 37 distinct sounds. The Japanese have hiragana, which represents 73 sounds, and they also have katakana, a different set of symbols that represent exactly the same 73 sounds, but for foreign words. Memorizing 37 or 73 symbols is reasonable. Memorizing 20,000 or more is not. In Japan, hiragana and katakana are not only teaching aids, they are also part of the normal writing system. The fact that the Japanese have created a special set of symbols for foreign words shows, in a certain way, how their culture is important to them. No surprise, then, that the Japanese market is one of the most demanding when it comes to internationalization. As just mentioned, Korean Hansa is now rarely used. The modern Korean language is called Hangul and is composed of 11,172 syllables, although only roughly 2,500 are commonly used. That's still a large and unwieldy number. But these syllables are mostly composed of only 51 basic components, called chamo. The chamo represent individual consonant and vowel sounds. For example, the two Hangul syllables shown on the slide are shown larger with individual colors to highlight the individual chamo, which are shown below. As you can see, the first syllable is written clockwise, the second top to bottom. Both the Hangul syllables and the individual chamo are encoded in Unicode. These are the hiragana and katakana syllabaries. The term syllabary is used rather than alphabet because each symbol represents a syllable, that is, a consonant followed by a vowel or simply a standalone vowel. For example, the highlighted letter is the symbol for the syllable no, which is very common in hiragana and may sometimes be useful to distinguish Japanese from Chinese, for someone who does not speak either. Katakana is mainly used to write foreign words, but both syllabaries have exactly the same 73 sounds, only the symbols differ. There is therefore a one-to-one mapping between hiragana and katakana, a bit analogous to the one-to-one mapping between lowercase and uppercase in English. Using either syllabary, you can try to represent your own name, but remember, every consonant must be followed by a vowel, so you may have to insert some extra vowels, which is precisely what Japanese speakers do when they learn English. The default is usually O or U. In fact, I once met an American who was asking about a Fat Boy Slim concert in Japan, and wasn't being understood until the Japanese fellow went, "Oh, you mean Fato Boy Sorimu." Here is a sample of Japanese text, and as you can see, it can be written horizontally left to right. This is not a contrived sentence, yet it contains 4 different scripts. First of all, there are English characters, BGS, which is a company name, and thus remains in English. The English is written in the Latin script, which is called Romaji in Japanese. What follows in parenthesis is a phonetic explanation of BGS that sounds like Baun Globaru. That is written in katakana because BGS is of foreign origin. Finally, you will see some kanji and hiragana characters. Hiragana is used for certain words and for inflectional verb and adjective endings. Hiragana also serves as a fallback if you've forgotten how to write the kanji character you want. These 4 scripts are what constitute everyday Japanese writing. Now, the more traditional display of Japanese text is top to bottom, right to left. You will note that English characters and some Japanese characters are rotated in this vertical display, but most Japanese characters are written the same without rotation. If you are doing software that has to do with desktop publishing, newspapers, or any kind of high-quality output, you will have to support vertical writing. Ruby are the small phonetic characters you see written above the ideographic characters in horizontal text, or written to the right of ideographic characters in vertical text. The ruby are traditionally used to provide the pronunciation, in hiragana, of the ideographic characters underneath. This use is common in Japan and is called furigana. Ruby using boppamofu characters is also seen in China, though less frequently. In the truly general case, ruby can be used for general annotation purposes and may be written just about anywhere. A complex Ruby spec exists for both HTML and CSS. Here's an example. An American company produced software for support centers. They translated their product to Japanese and sold it in Japan. Unfortunately, the software did not support Ruby. Imagine the scenario. The support person answers the phone, sees the customer's name on the screen, and says, "Hello, Mr. He can't read the name properly because the name is rendered in ideographic characters, which the support rep has never before seen. In Japan, a culture that puts a premium on respect, a customer support encounter which doesn't allow the rep to recognize or pronounce a customer's name properly was, of course, a major failure. The moral of this story is that it is always important to understand the needs of your target market before you try to sell them a product. In Japan, it is often essential to capture phonetic information at the time of data entry and later display it where appropriate. Again, on this notion of what you can pronounce versus what you can write, the next two slides are actual scans of a Chinese phone book. Now, the Chinese phone book has two parts. The first part, shown here, is sorted according to pinyin. Remember that pinyin is a transliteration of Chinese into Latin script. It reuses 25 of the 26 letters of the English alphabet, but adds a few things, so the categories here are not A, B, C, D English, but rather A, B, C, D pinyin. Further down, V would be missing, and you might see a U umlaut category. The idea here is that if you meet somebody in a bar in China, and that person gives you their name, you hear the person's name so you know how to pronounce it, but maybe not how to write it, because the same sounds can be written different ways. So you would use this part of the phone book sorted phonetically. On the other hand, if someone hands you their business card, you see the name, it might be an old historical family name, so you can't necessarily pronounce it, and the phonetic sort shown here is useless. That's why there is a second part to the Chinese phone book, which is sorted visually by stroke count. The categories you see now are 0 strokes, 2 strokes, 3 strokes, 4 strokes, etc. The names are stored based on the number of strokes in each character. The 0-stroke category is used for Latin characters. So, for certain applications in Asia, you need to support both phonetic and visual sorts for large datasets, in particular for phone books. Another question with Asian languages is, how do you type them in? One possible answer is a keyboard with a lot of keys, as we have here. It takes a few years to master this device, which has a few thousand characters arranged so the most frequent characters are grouped in the center. On today's computers, input methods are used to facilitate ideographic input, but it still requires several steps. The next slide will show you how that works. Let me show you how Japanese input works on a Windows PC. I'm going to input Japanese right here into a PowerPoint slide in edit mode. I'll be using the Microsoft IME, which stands for Input Method Editor, although today we say simply Input Method. First, please notice at the bottom that I have made the language bar floating on top of the slide in order to make it more readable. When minimized, the language bar is just next to the system icons on the taskbar. What I want to do is enter a kanji character that is pronounced okuru, and I want to enter it using a phonetic method with hiragana characters. One of the issues here is that with the many thousands of kanji characters, many of them have the same pronunciation. For example, okuru corresponds to several kanji characters: happen, or fire, or prosperous, and others. I'm going to follow the steps of the demo as described here. First, I switch the input language from English to Japanese. You can see that there are several options for the Microsoft IME. In particular, I need to set the input mode to hiragana input. Now, since I want to type okuru, I start by typing O, and I immediately get the hiragana O. You may remember that hiragana and katakana represent syllables, or single vowels, but not single consonants. Next, I type K, and I get a K because there is no individual isolated K sound in hiragana. The IME is waiting for a vowel to complete the hiragana syllable. So, when I type O, I get the hiragana symbol for ko. Then I type R, and I get an R, and when I type U, the hiragana ru is displayed. So now I've got okuru, written in hiragana, and if that's what I wanted, I could hit the Enter key and be done. But I want to enter a kanji character, so I hit the spacebar, and the IME displays the most likely kanji okuru that it can. Again, if that is the okuru I wanted, I could hit Enter and be done. But it turns out that the kanji okuru that I want is yet another one, so I hit spacebar again. This time the IME displays a list of okurus, and on the right-hand side, those with book-like icons even have some associated dictionary information to help me choose. Finally, I select the okuru that I want, hit Enter, and we're done. In the previous demo, it looked as if PowerPoint had an embedded input method, because everything worked so seamlessly. In fact, everything you saw happened in an invisible window on top of PowerPoint, acting as a temporary editing area. And this is why input methods, historically, have been called IMEs, input method editors. The intermediate editing appeared seamless because PowerPoint is an IME-aware application. It provided the IME with information on cursor position, font style, size, color, etc. To make this more obvious, let's try now with UltraEdit, a programmer's editor which is not IME aware. I have already set the UltraEdit font size quite large, and the input method is already in hiragana mode. Let's see what happens when I type okuru. O-ku-ru. As you can see, it works the same as before, except now the characters are not of the same font size or baseline as the editor. Because UltraEdit is not IME aware, it has not provided the IME with all the information. In fact, if I move the cursor around, you can see that the IME follows the Windows cursor. Nevertheless, I can still hit spacebar once, then a second time. There is still some dictionary information, and I can pick the okuru that I want. At this point, the Japanese characters are still inside the IME. UltraEdit has not seen them yet. The IME will send them to UltraEdit only when I hit Enter, and then UltraEdit displays question marks, one for each Japanese character received. That's because the file is an English Windows file. In the English Windows character set, that does not support Japanese characters. The question marks represent character conversion errors. We'll see more about this later. Let's now consider another class of problems, which are well illustrated by the Arabic script. We'll start with contextual shaping, that is, characters that change shape based on context. Other languages, such as Greek and Hebrew, also have a few contextual characters, but in the case of Arabic, almost all characters have contextual shaping. This is the Arabic letter Ain, which, when typed on a keyboard, appears as you would expect on the screen. But now if I press Ain a second time, you'll see that we get a different shape on the screen. And in fact, the shape of the first one displayed has also changed. If we press Ain a third time, then hit the spacebar and press a fourth time, we now have the four possible shapes of the Ain character: the initial, medial, final, and alone shape. This is not like uppercase and lowercase. This is only one character that can have up to four shapes. We call these shapes glyphs. A font is simply a set of glyphs. Take a good look at how these Arabic characters get displayed. The letters change shape. Some are displayed below, others display above, others combine above, etc. This is what we mean by a text rendering algorithm. For many scripts, such as Arabic, Thai, or Devanagari, the whole issue of displaying text on the screen is very complex. The very simple idea that a keystroke A corresponds to a character A in memory and corresponds to a glyph A on the screen, while true in English, does not hold for all other languages. The reason why the Arabic writing is contextual and cursive is because, in the Arabic culture, the writing of the Quran, the Holy Book, is sacred. Contrary to English, where we have a printed form and a written form, in the Arabic world there is only one form of writing, the form of writing from the Quran. Also, because in the Muslim religion you're not allowed to represent human beings or animals in visual arts, most of the artistic energy of the Arabic world is diverted into writing and poetry. Perhaps you are familiar with Khalil Gibran, who wrote The Prophet, one of the best-selling books of the 20th century. When you buy an Arabic plate or an Arabic carpet, and you see some fancy designs on it, this is not a picture. The fancy designs are always some form of writing. It can be religious. For example, Muhammad is the messenger of Allah, as this one here is. It can be about life, about love. But every piece of Arabic artwork that you buy actually is a written message. Here is an example of three-dimensional poetry, as it were. This particular piece says, "Leave for me, into the dark unknown, a window." This is a fairly interesting art form because it works on two levels. It provides beauty at visual and conceptual levels at the same time. These examples highlight some of the unique characteristics of the Arabic culture. As translators care about the beauty of words, Arabic calligraphy celebrates the beauty of writing. Let's move on to the issue of bidirectionality. Here we have two Arabic letters, which spell the word call. And now I'm going to type the numbers 1, 2, and 3. Watch what happens. 1, 2, 3. If you've paid attention, you've seen that the letters are going one way and the numbers are going the other way. This is what we mean when we say that Arabic is an inherently bidirectional script. Even before you mix Arabic with English or French, there are two different writing directions within Arabic itself. If you do mix Arabic with English, French, or any other left-to-right language, things get really interesting. Indeed, let's see just how interesting by considering the inherent complexity of bidirectional processing. Here we have a simple example of Arabic, reading right to left, with numbers reading left to right. The next example illustrates Arabic with an English word inserted. The English text, like the Arabic numbers, is displayed left to right. We could also have two-column text with English on the left and Arabic on the right. The English text could have some Arabic inside, which would of course display in its natural right-to-left direction. Or finally, we could have this more complex case, with the first example embedded completely within the English text. Now, if you take a look at what's happening in this last example, you'll see that English is being displayed from left to right, and that the Arabic sentence is being displayed from right to left. Inside this Arabic sentence, we have an English word, and we have some Arabic numbers, both of which are going left to right. Inside the English sentence, however, things are a bit more complicated. We have the complete Arabic sentence from the first example displayed right to left, and inside the Arabic sentence, we also have Arabic numbers going left to right. What you're seeing here are multiple levels of directional embedding, and it can get worse. I could take this whole English sentence and paste it into an Arabic paragraph. I could then take that Arabic paragraph and paste it into an English page. In fact, the Unicode bidirectional text rendering algorithm allows up to 125 explicit embedding levels. This was recently increased from 61 levels, because apparently 61 simply was not enough. This is the main problem in supporting Arabic, Hebrew, or other bidirectional languages. The directional issues are the ones that cause a lot of problems. As we just said, directional issues are difficult. In fact, they are arguably the most difficult issues in internationalization. To illustrate this, let me show you something as basic as selecting text, but on the English string with embedded Arabic that we just saw. As the slide says, I'm going to select one character at a time in the purple text shape. I'm going to hold down the Shift key and then press right arrow many times, calling out each time. Right, right, right. As you can see, we're selecting normally. Right, 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 right. And the selection moves to the next letter on the other side, which actually makes sense because it is the first letter of the Arabic insertion. Right, right, right. I'm pressing right but going left. Right, right. And again, the selection jumps to the first number in the numeric insertion inside the Arabic insertion. Again, this sort of makes sense. As I continue to hit the right arrow, we work our way out of the Arabic insertion. I can also unselect by hitting Shift left arrow many times, and we see how it unselects. With Unicode, the data you see here, English and Arabic, is stored in memory in logical order, which is based on the order of pronunciation. The behavior observed matches the logical order in memory. It makes things simpler for the programmer because the selected region is always a single contiguous region in memory. If we allowed the user to select a contiguous area on screen, then the software would have to deal with the fact that the selected screen area corresponds to multiple distinct regions in memory, which is doable, but a lot more trouble. Finally, we see what happens when I move the mouse very slowly over the same text. I'm going left to right here, and I'm going to go backwards now. I've spent 13 years working with Arabic BiDi issues, and this mouse behavior still gives me a headache. The ergonomics of this Microsoft solution are not really designed for normal human beings. They are constrained by implementation considerations. Java, for example, does things differently, but it's also imperfect and has bugs. It's simply that BiDi handling is very difficult, and what we've shown here is just the tip of the iceberg. The Unicode BiDi algorithm has 50 rules applied in a specific sequence, and the description they provide is for implementers. What is supposed to happen in user terms is simply not specified. This is why we have a dedicated workshop on Arabic and BiDi issues, which contains the only complete user-oriented explanation of the BiDi algorithm. Here we summarize the directional behavior of scripts. Latin, Cyrillic, Greek, and for common applications, Chinese, Japanese, and Korean scripts, namely Han, Hangul, Katakana, Hiragana, Bapamofo, all can be written horizontally, left to right, top to bottom. For desktop publishing, however, and other applications needing high-quality presentation, Asian scripts are written vertically, top to bottom, right to left, and often there will be a mixture of vertical and horizontal writing. Mongolian is a bit of an exception, being top to bottom, left to right. And finally, we have the Arabic and Hebrew scripts, which are bidirectional, but mainly right to left, top to bottom. The blue box shows the area of lower risk. As soon as you leave this area, as soon as you want to handle other directions than left to right, things get much more complex. Now we'll look at a few text processing functions that change from one language to another. Sorting is one of the most language-dependent issues of all, and sorting is extremely complex. It deals with every conceivable aspect of characters you can think of. In Chinese, among other things, characters can be sorted based on the number of strokes in the ideograph. In Japanese, phonetic sorting is often used. In French sorts, when two words have the same base letters, accents are used to determine the correct order, but they are considered from the end of the word moving backwards. There are all sorts of strange rules for sorting. So the bottom line is, never try this at home. There are sorting tools available on all platforms. When you use an existing sort, you should remember to reflect the features of that sort in the GUI. For example, in Japanese, the difference between hiragana and katakana is just whether the word is foreign or not. The pronunciation is exactly the same. So, for a Japanese phonetic sort, it makes sense to have an option that ignores the hiragana-katakana distinction, the same way we typically have an option to ignore case in English. There are major software companies that have not added that option to their applications. Perhaps the most important thing to remember when you are sorting is that you are not sorting for the data or for the server, but for the audience. Once again, the concept of audience is essential. The purpose of a sort is to allow the human being to find things in the order he or she expects. So, a database of European customer names will be sorted differently for a German user, a French user, or a Swedish user. This has significant implications for databases because it means you cannot optimize an index for all audiences at the same time. This is a slide from our Java Internationalization workshop. It shows how Java sorts the same 13 Asian characters according to the locale. As you can see, all 4 Asian locales are distinct for these 13 characters. And remember that in their daily lives, people use about 2,000 characters of the 20,000 or more. Providing a correct locale-sensitive sort is critical. There's no way around it. Moving on to justification, this slide illustrates a fairly extreme example. I've put in lots of white space between the English words to illustrate inter-word justification. And in Arabic, you'll notice some extended connecting lines between characters inside the words. These connecting lines are called kashida, and CSS3 once supported a text kashida space property that specifies the percentage of kashida expansion versus white space expansion. The example on this slide shows 100% kashida expansion, which is a traditional Arabic style. In many cases, it's pretty simple to wrap text. All you have to do is find the spaces between words. For languages based on Latin, Greek, Cyrillic, or Korean scripts, that's generally the case. There are some languages, however, where hyphenation is more important. German, for example. Arabic and Hebrew also have spaces between words, so programmatically they are not any harder to wrap. The only problem is that, visually, for the user, the results can be extremely confusing. The problem is that some languages don't have spaces between words. A sentence is just a stream of characters. That's the case in Chinese and Japanese. Fortunately, text wrapping conventions in Chinese and Japanese can be expressed by simple rules, such that certain characters are not allowed at the beginning of the line and certain characters are not allowed at the end of the line. These rules give rise to 3 standard wrapping algorithms, which is acceptable for most applications. The really complex case occurs with Thai, Khmer, and Lao. In Thai, for example, there are no spaces between words and there are no simple rules. The only way you can wrap a Thai text is to use a Thai dictionary and try to figure out where the words start and stop inside the text. So when a program starts working in Thai, it might all of a sudden need more memory to load the Thai dictionary. Here we have a web page containing some Latin text, English, French, and German in fact. If I shrink the window width, the browser wraps as you would expect. That is, at the spaces between words. In Arabic, there are also spaces between words, but wrapping bidirectional text produces strange effects. In Japanese, text mostly wraps a single character at a time, but there are certain characters, such as a closing parenthesis, that are not allowed to start a line, while the opening parenthesis is not allowed to end a line. In Thai, there are no spaces between words, and there are multiple characters per word. Thai text wraps one word at a time with the help of a Thai dictionary. And finally, because you can declare the language of each paragraph in HTML, the browser can actually wrap all these examples at the same time. Search today is a big thing, and I don't just mean Google or Bing. With the information explosion, companies need search just to find things internally. Most company websites now offer search functions, and don't you hate the ones that don't? So search is important. Unfortunately, it's not always easy to figure out where words start and stop, not only in Thai, Khmer, and Lao, but also in German, Japanese, and Chinese. The first example shows Germanic agglutination, which can compose very large words. This word says life insurance company employee. Parsing these kinds of things is not trivial, but not too hard either. The real challenge is with Asian ideographic data. The example below reads as Chinese literature, but it could also be Middle Country Language Study, or it could be Chinese Language Study, or Middle Country Literature. It could be looked at various ways. For the purposes of search, since you don't really know which is most pertinent, you have to accept them all. Wrapping is solved by simple rules in Chinese and Japanese, but searching is quite difficult. The fact is, searching Asian text really is rocket science. People write doctoral dissertations on how to best handle Chinese searching. In fact, there was at least one company, Basis Technology, that specialized in this area. Both Google and Microsoft were at one point licensing their technology. Of course, Google eventually built their own. And here is a real example. A company I was helping had received this mail from an unhappy Japanese customer who was complaining that the search was not working properly because a whole word search for horse was also returning a bunch of unwanted results. The irony of internationalization is that English really is a very nice, simple language with small words, no accents, and no shaping rules, etc. And what that means is, as we go forward, things can only get worse, right? Cultural aspects change even between countries that speak the same language. We'll look at some examples. We'll start with system of measurements. The measurement system is not the same between the United States and the rest of the world. The United States uses a system based on English units that is called the United States Customary System, or USCS. The imperial system was also derived from English units and is almost identical to the USCS except for volume units. USCS ounces are slightly bigger. The difference is that 16 imperial ounces of water weigh 1 pound, but in USCS units, what weighs 1 pound is 16 ounces of wine. Isn't that wonderful? The measurement system itself was based on wine. The rest of the world uses the metric system, which is also based on water. Furthermore, even the 3 holdout countries have officially announced metrication plans, but they are progressing very slowly. Some areas, though, are largely metric. The U.S. military uses metric units extensively because of interoperability issues with NATO and other forces. NASA in 2007 went officially metric on the moon because it collaborates with the space agencies of a dozen countries. Numbers are not formatted the same way. There's a good deal of variation both in digit separators and decimal separators. In this table, you'll see periods, commas, and even spaces playing either role. The most interesting case is in Hindi, where digits are grouped by 3 and then they are grouped by 2. So not only is the grouping different, but it's a variable grouping. Another interesting fact is that English Canadians and French Canadians don't use the same notation. The potential for confusion in a bilingual city like Montreal is very real. A man who had lost his life savings in a financial scam was reimbursed $86,000 by an insurance company, only to have them take it back a few days later and issue him the correct check for $86. Currency formats are highly variable. Currency symbols and their placement differ, as do decimal and thousands separators, and the number of decimals. Here are a few examples. First, the well-known dollar format used in the United States. English Canada uses the same format and dollar sign, but it represents Canadian dollars. French Canada uses the same currency, but a different format. The dollar sign is placed after the number, the decimal separator is a comma, and the thousand separator is a space. This shows that currency format depends on locale, not country. The Economic and Monetary Union, EMU, of the European Union includes 20 countries that share the euro currency. Most of these countries use a decimal comma, but Ireland uses a decimal period. This shows that currency format can vary for the same currency. Cabo Verde is unique in that the currency symbol is used as the decimal separator. Here, the dollar sign represents the Cape Verdean escudo. In Lebanon, hyperinflation has rendered the two decimal places useless, so they are no longer written. Note that the currency symbol may have several characters. In Kuwait, the dinar is displayed with 3 decimals. In Japan, the yen never has decimals, although decimals appear when quoting exchange rates. Finally, note that all these currencies have ISO 4217 standard identifiers, which are useful for international transactions. Date and time formats vary widely. The U.S. is fairly unique with its month, day, year format, and because we use a different format in Canada, the opportunities for confusion are endless. I once exchanged a hard drive that I thought was under warranty, only to be billed $300 because the month and day were reversed. Time zones are relatively easy to deal with, but if you don't deal with them, and many people don't, you can create some amazingly twisted problems. In this slide, you'll see that when it is 6 a.m. in San Francisco, it is 9 a.m. in New York, and it's 10:30 a.m. in Newfoundland. At the same time, it's 7:45 p.m. in Kathmandu, Nepal, which is one of the most peculiar time zones in the world. And it's also 1 a.m. in Australia, but it's 1 a.m. of a separate day, of a separate year, in fact, of a separate millennium. The point here is that the time zone doesn't just affect the hour of the day, but it affects the entire date object. To avoid problems with time values in databases, you should always store time in UTC, or Universal Coordinated Time, which is the new name for Greenwich Mean Time. If you need to guarantee reproducibility of the original time information, you can use a UTC with time zone format. Calendars also change from one place to the next. For example, the year 2018, according to the Common Gregorian calendar, corresponds to year 5778 in the Hebrew calendar and spans years 1439 and 1440 in the Islamic Hijri calendar. And yes, the Gregorian calendar is understood everywhere in the world, but that does not mean it's the preferred local calendar. You'll notice that the Hijri calendar is lunar, with years of 354 days. This means that everything shifts by 11 days every year, so that New Year's Day or Ramadan can be in the middle of summer or winter. The Hebrew calendar also includes lunar months, but adds an extra month every 2 to 3 years to align with the solar year, ensuring stable seasons and holidays. You'll also notice by looking at this table that calendars are tied to the lives, deaths, and coronations of prophets or rulers, like Christ, Mohammed, Buddha, or King Salabhana. The Japanese calendar is also based on a ruler, but it is an era calendar based on the current ruler, so the numbering of years restarts every time a new emperor comes to power. The way it works is that when a Japanese emperor comes to power, he names his era. The last emperor, Akihito, came to power in 1989 when his father Hirohito died, and named his era Heisei. So 1989 was year 1 of the Heisei era. In 2019, Akihito abdicated, and his elder son Naruhito ascended to the throne, starting the Reiwa era. So, 2024, for example, would be year 6 of the Reiwa era. If you're wondering if these calendars are actually used, here is a real tax form scanned in Japan. You'll notice 2 date entry fields on the left. They are each composed of 2 parts. The first part provides a list of short era names, and the user must circle the proper era. The second part is a more usual year, month, day field where the user enters numeric values. There are 4 different names of eras, because if you want to cover, say, 100 years, you need 4 emperor eras to cover that long. These 4 eras actually go back to 1868. If you look to the right of the slide, you will now see 2 more date entry fields. Note that these fields have only one era, the current era in fact, which is Heisei and not abbreviated. This may occur if the form is requesting the date the form is being filled, the current date in fact. Only one era is required because the current date is always part of the current era. Paper sizes vary from one place to another. This is an A4 document, and this is a letter document, both displayed to scale. You can see that if you were willing to sacrifice only a small 1/4 inch on your right margin, you could distribute your documents in Europe and never ever have to worry about reformatting. This is a good example of internationalization. Sometimes a tiny, tiny compromise early on can avoid a lot of grief down the road. One more thing you can see in the table is that Mexico and a few other countries have officially adopted the ISO A4 standard, but North American formats remain in widespread use. Phone numbers? Don't even try. Phone numbers in China alone can be from 4 to 15 digits long depending on the city, the province, the pager, the cell, the home, the company, etc. To be fair, it is possible to correctly and completely format and decode phone numbers. Android does it, for example. But you need to set up a descriptive language, an update mechanism, and be warned, it can involve 2 person-years of effort. This is what a generic address looks like in Japan. It may potentially include the postal code, prefecture, city, ward, district, block, subblock, and house. So, if your web form asks for city, state, and zip, how that gets filled is fairly random for a Japanese user. There are actually people, companies, who will sell you software to convert such random input to a meaningful address. So you might well ask, why not simply display to the Japanese user a standard Japanese address input form in the first place? There's a fellow called Graham Rind who has written a few books on address management and who sells metadata to help you achieve this. Click the link below the slide title for more information. Colors are extremely significant, but they mean different things in different places. Black is a cool color for websites in the US, but black is not at all cool in Asia. While red means danger in the West, it means joy in China. So a big red flashing warning sign may actually go completely unnoticed in a Chinese context. Here's an example from the Chinese stock market. Stocks go up in red, down in green. In the Western world, colors would be reversed. In fact, being in the red is usually not a very good thing. The bottom line is that from one culture to the next, anything can change. This is what I call pervasive diversity. Now, this may seem complex and troublesome, but in fact, it's a tribute to who we are. And as globalization professionals, what we are trying to do is to preserve the richness of who we are. And that's a nice thought, because we're not building weapons here. We're not polluting the planet. We're trying to preserve human culture as it encounters computer technology. In Star Trek terms, we are the guardians of humanity. We will not be assimilated.